So in the last class, we have seen that fundamental group of figure 8, right? If we use Van Kampen theorem, then we can conclude that its fundamental group is free product of two copies object, that is free group generated by two elements. Next, we consider following example. Right. So let X be the union of n circles with a single point in common, where n is greater than 2. For n equal to 2, if you take two circles, for n equal to 2, so what will you have? You have two circles with one point in common. So something like this. Right? It is what? It is figure 8, you can see. Or you can say that it is homeomorphic to figure 8. So, but we have seen that its fundamental group is free group generated by two elements. Now, if we have n such circles which have exactly one point in common, right? So our space should look like right, another circle. Okay, so here means we have taken four circles with exactly one point in common. So similarly, we can have n circles having exactly one point in common. So exactly we have x equal to a1 union a2 union an, where each ai is homeomorphic to S1, right? And if I is not equal to j, then ai intersection j equal to exactly this point x naught, right? So this is point x naught. So we will use induction to compute its fundamental group. So we will use induction on n to compute that we will use induction on n to prove that. We'll prove that pi 1x is a free group, free group on n generators. Alpha 1, alpha 2, alpha n, where alpha I is represented by a path that goes around the circle, by a path that goes around the circle once, right? So this, what are these alpha 1, alpha 2, alpha n? They are loop classes, right? And this alpha I is and this class alpha I represents the loop that goes around the circle AI once, right? So if this is A1, right, then alpha 1 will be the class of this loop. Similarly, if it is A2, then alpha 2 will be class of this loop. Now, we have already proved this in the case when n equal to 2, right? So we have already proved this for n equal to 2. Now choose a point AI in the circle capital AI such that AI is not equal to x naught. So x naught is the common point of the given circles, right? Now put u equal to capital X minus an and v equal to capital S X minus a1, a2 and so on, an minus 1. Okay. So u is the so this u and v are actually open sets. Then clear similarly U and V are open sets. And you just see here that you have things like these. Right? So suppose this is your AN, right? So if you just, this is your small AN, and this is suppose AN minus 1, right? Suppose this is A1, right? Then A2, and then dot dot like this. Then here you will have, you can choose here somewhere AN minus, small AN minus 1, right? Here you can choose A1, right? So in this X, from X, if you just remove this point AN, right, then you will get an open set. Okay. Whatever you will get, that will be an open subset of X. Similarly, if you remove these n minus 1 points from X, then also you will get an open set. And you just see, if you consider this U in which you have just removed AN from this X, then what will you have, right? So you will just have something like this. And even point removed. So what you can do, you can just, this portion you can slowly you can shrink to this point, and this one you can shrink to this point. It means that what will you get after shrinking? What will you get? You will get A1 union A2 and so on union AN minus 1. This AN will not be there, right? It means what? It means that this U deformation retracts onto this A1 union A2 union and so on AN minus 1, right? And A1, this U deformation retracts onto A1 union A2 and so on union AN minus 1. And now what you do is, if you consider V, right? So V is the one which is obtained by removing A1, A2 and so on AN minus 1 from X, right? So so you just see that so if you remove A1 from this capital A1 and then A2 from this capital A2, then you will have something like this. And similarly here, this one. And then again this one. Right? So you can see that these ones, you can shrink them slowly and slowly to this point, similarly this one. So all of them you can shrink to this point, and ultimately what will you get? You will get just this one, right? That is AN, right? So what is exactly this? This is your V. So V you can deformation retract into onto this AN, right? So V deformation retracts onto En. And U intersection V, right? What is U intersection V? In U intersection V, you will have this also, right? So from AN also, so all the, right? So from AN you remove small an, from A to A1 you remove small a1 like this, right? So all of them you can sync to a point, right? So what will you have? So U intersection V is this, and U intersection V uh, can be contracted to a single point, is contractible. So we can use Van Kampen theorem. So what you have? You have this U, right? V, right? X equal to U union V, right? And U intersection V, it is contractible, right? And hence it is simply connected. So what you have? You have that pi1 X, right? Is free product of pi1 U and pi1, right? Hence, because again, this so the quotient that you have by using Van Kampen theorem, that n will be generated by elements. You had I alpha beta, omega I beta alpha, omega inverse. But where omega is from, where omega is from pi 1 U intersection V, but this is trivial group. So omega is trivial, and hence those elements will be trivial, and hence n is going to be trivial. So this is basically your this. Hence, by using Van Kampen theorem, uh, phi x naught is uh, the free product of pi 1 U and pi 1 V x naught. Now, because U deformation retract unto A1 union, A2 union, and so on, AN minus 1, and V deformation retracts unto AN, uh, uh, since pi 1 U x naught equal to, I can say, isomorphic to pi 1 A1 union AN minus 1 x naught and pi 1 V x naught pi 1 n x naught, we have pi 1 x is isomorphic to pi 1 a1 union an minus 1. So we can skip this base point because all the spaces are path connected, and if you have path connected, then base point becomes immaterial, right, for the fundamental group, because at each point this fundamental group will be same. So this star pi 1 an. Now we can use induction hypothesis. So what to apply induction? What hypothesis we have to have, right? So first thing that when n equal to 2, right, result is true, right? Uh, Suppose that result is true for sorry. So when k equal to 2, result is true, right? That is for if x is equal to a1 union a2, then result is true. Already we have seen. Now suppose that result is true for k equal to n minus 1. Okay. Then what we have? We have this fundamental group of this is fundamental group of this. Direct means free product with fundamental group of this, right? So you can use induction hypothesis. So by induction hypothesis, this pi 1 x equal to pi 1 a right? Hence pi 1 x is simply, so this is exactly this. So what we have, this is nothing but I to n pi 1 ai, right? Okay. And you know that this how we concluded this, and each pi 1 ai, because ai is isomorphic to s1, this is basically z. So pi 1 x is pre-product of n copies of z, or pi 1 x is free group generated by n generators. Next. So we'll talk about fundamental group of torus. It is denoted by T, and we have seen that T is isomorphic, homeomorphic to S1 cos S1. So fundamental group of torus can be realized as direct product of this, which is isomorphic to Z. So here we will use Van Kampen theorem, and we will prove that this is exactly this, right? So this is some kind of verification. So we have already proved this. We will again use Van Kampen theorem to establish this. So for that we will realize torus T as identification space of this square, where this side is identified with this side and this side is identified with this side, and this is x naught vertex, this, they all will be identified. Then we will define so torus will be so this is your torus when you identify this with this S and this is with this is. Now we choose a point y in the center, and let u equal to t minus y and be the image of the interior of the square under the identification. Okay, so this interior portion, right, it remains as it is. Only these edges are being identified, right? So V is the interior, this interior, right? Now clearly U and V are open sets, but open subsets of this T, right? and this U, V and U intersection V are path connected. So this also should be there for in order to apply Van Kampen theorem, path connected. Now, because B is the interior, so that is homeomorphic to an open disk, and open disk is contractible. So this uh, V is uh, simply connected because it is homeomorphic to open disk. Now we can apply Van Kampen theorem. So by Van Kampen theorem, so Van Kampen theorem can be applied, and fundamental group of T is isomorphic to pi 1 U star pi 1 V, right? Quotiented by N, right? So we know what is N. N is the normal subgroup, generated normal subgroup of this free product of this and this, generated by elements of the form I alpha beta omega, I alpha beta omega inverse. Okay. Now now what we have here is this V is uh, simply connected, since V is simply connected, since V is simply connected, pi 1 V, its fundamental group is trivial, hence N is generated by elements of the form here we can write this phi omega, where omega belongs to pi 1 u intersection v, and phi from pi 1 u intersection v to uh, pi 1 u induced by, it is induced by the inclusion map u intersection v to u, right? Because the other one, right, this uh, because I, so this I alpha beta, right? So if you consider the homomorphism induced by inclusion map of this into V, right? So that induces the trivial zero homomorphism, right? So this from pi 1 u intersection V to pi 1 V, because pi 1 V is trivial group, right? So this phi2 will take everything to 0, right? So here this you can consider phi2, right? So this is always 0, right? So n is going to be generated by elements of this form, right? That is this, where omega is here and phi is from here to here, induced by this inclusion map. Now now what is this pi 1 u intersection v? Since u intersection v is what? It is the open disk with one point y removed, right? So if you have an open disk, all right, so with one point, maybe the center removed, so this deformation retracts onto a circle, right? And hence since this deformation retracts onto a circle, uh, pi 1 u intersection v equal to z. Okay. Now so this is then so if I choose, right, so in this u intersection v, if I choose a loop, right, if I choose a loop, so if I want to talk about fundamental group at x naught, sorry, uh, so this is suppose x1, right? We can consider a path D joining x0 and x1. Now, under this map, phi, right? So phi, when you map this, consider this map phi. So phi, if you map this from pi 1 u intersection v to pi 1 u. So what is pi 1 u first? So this deformation retracts onto a circle. So this is Z. Now U deformation retracts so what is U? U is just the this torus with one point Y removed. So this you can slowly and slowly you can deform it to get this only, right? And with this identified with this and this identified with this. So when you have something like this, and if you identify this with this and this with this, you can verify that you will get figure 8, right? So when you identify this with this, what will you get? You will have something like this with like this, and here you will have something like this with this. Okay. Now if you identify this one with this one, so this is identified with this. So this one and this one will go together, and you will have this, and then this, right? So like this, like this. Okay. So ultimately, you will get a figure 8. So U deformation retracts onto figure 8. Right? Hence pi 1 u is Z star Z, right? We have seen that fundamental group of figure 8 is free product of two copies of Z. Now you see how this map phi works, right? So if you take a loop here, right? If you take a loop here, how it is going to be mapped? So this when you consider the homomorphism here, so consider the loop class of this, right? So this is going to be mapped to, so first you go this, right, and then through B, and then you go to A inverse, right? So you have to have something like, if you have something like this, right? So this is A and this is B, right? So first it will go A, and then it will go to B, and then opposite in the opposite side B A inverse, and then again in the opposite direction B inverse. So this loop will be mapped, right? So this loop will be mapped to A B A inverse B inverse. Okay, so this if you consider take the generator of this, right? Suppose that is omega, then it is going to be mapped to A B A inverse B inverse, right? So basically, this n will be generated by elements of this form. So n is generated by uh, this we can write uh, alpha beta alpha inverse beta inverse, where alpha and beta are represented by the loops. So these alpha and beta, they are loop classes, are represented by the loops A and B respectively. And this is pi 1 V is simply trivial group, and pi 1 U is Z star Z. So we have this isomorphic to Z star Z quotiented by n, where n is generated by n is normal subgroup generated by this, right? So thus pi 1 T, it can have this, it can be represented by generators and relations. So what will be the generators? So loop class of this and loop class of this, right? So alpha beta and then alpha beta alpha inverse beta inverse, right? So this is the relation. So what does it mean, right? So how it comes to Z cross Z, right? So if your if your alpha beta alpha inverse beta inverse, if this comes out to be identity, right? These are the relations, means this will come out to be identity in the fundamental group of pi 1 T, right? This implies you just multiply by beta in the right side first, then and then by alpha, then we will have beta alpha. Okay. Now it means that these two generators alpha and beta, they commute. But if the generators will commute, then the group will be commutative, right? If generators will be commutative, then group also will be commutative. So, what we are going to get, hence pi 1t is commutative, and this is going to be Z cross Z. So you just see here that if you have two generators which commute, right? If you have two generators alpha and beta which commute, then uh, the group generated by them is going to be alpha to the power R1, beta to the power R2, R1 and R2 belonging to J, right? Because of this condition, all the words will reduce to a word of this form, right? All the words in the Z star Z will reduce into this form, right? But this is nothing but Z cross Z. Next example, real projective plane P2. Real projective plane P2. So how it is how it looks like. So if you just take a circle, right, and basically disk, right, closed disk. Take a closed disk and identify the opposite antipodal points, like so, like this. This you identify with this you like this. Then whatever you will get, that is called real projective plane P2. Now, how we are going to compute a fundamental group of real projective plane? So what we'll do, we consider we can divide the, so this, let me write it. So just this circle in the disk, right? So we can divide this into two parts. We can consider this x0, that they will be identified, and this is one arc A, this is another, right? So this will be identified with this will be identified with these, like this, right? So this will go to here and like this. Now, here also we can remove a point from here. Suppose that is y. Then we can take u equal to P2 minus y, and v we can consider image of the interior of the polygon, right? So here this we can consider this to be a polygon, right? So of course it will be this it will be homeomorphic to a polygon. Or here, because I am taking circle, I mean disk, image of the interior of the disk, under the identification. Now again you can see that that's pi1 v is trivial, and this u and v also are open. U, v are open, path connected, and u intersection v is again this open disk with the point y remote. U intersection v is path connected. So we can use Van Kampen theorem, and you can also see that this. So almost everything will be similar to the case of torus, except the this phi from, except the homomorphism phi from u intersection v to u, right? So pi1 u is going to be what? It is going to be a you just see, if you u is u deformation retracts, onto a circle, because when you just first of all this deformation retracts onto this boundary circle, and when you identify this with this, you will get again a circle. So this is going to be z, and again pi1 u intersection v is z, right? But you see that this phi, right? Phi from pi1 u intersection v to pi1 u, this takes, if we take any loop, right? If we take any loop, then this is going to be mapped. First it will be mapped, it will go through this, and then this will again go through this, right? So this if this class of this loop A, right, so is given by alpha, then this class of this loop will be mapped to alpha square, right, because it goes twice. So if suppose the class of this gamma, so here gamma goes to square, okay. So by Van Kampen theorem, we have this pi1 p2, this is going to be isomorphic to Z, right? So there will be one pi 1 u star pi 1 v. So pi 1 u is Z, pi 1 v is trivial group. So we have uh, Z quotiented by the normal subgroup generated by this alpha square, right? So we have representation of this group by generators and erasers like this. So this is basically nothing but Z2. So next, similar ideas we can use uh, for connected sum of n torus, right? Uh, or genus n orientable genus n surface. So what is connected sum of n torus? So you have a torus like this, right? We have another torus, right? We have another torus here, right? So you can get connected sum of these two. How will you do? You can just remove a disk from here, and you can remove another disk from here, and you can just glue these two through this one. So you will have something like uh, this. So here you have glued here, right? So through this, similarly you can have this is connected sum of two tori. Similarly, you can have connected sum of n tori, right? So you can have something like this. Right? So for example, this is connected sum of 1, 2, 3, 4 tori, right? So we will be talking about fundamental group of these in the next class. So idea will be same, right? So we will stop here.